So this video is going to begin with a review of the shell model that we've been developing, and then we're going to take the model to the next step. So it turns out that the shell model is really useful for chemists. Let's remember where we developed this model. So we started out by looking at, well, ionization energies, but then we got more sophisticated and we're using photoelectron spectra like this. So this photoelectron spectra with 3 peaks tells us that we have an atom with 3 energy levels. These peaks, their relative peak heights are 1 to 1 to 3. So if this were an atom with 7 electrons, then to get up to 7 we would have to have relative number of electrons 2 in this energy level, 2 in this energy level, and 3 in this energy level. Well, that corresponds to this electron configuration down here, 1s2, 2s2, 2p3, and that's for nitrogen. We might imagine that this picture, this photoelectron spectra, translates into this picture. So here's the nucleus in grand scale. It's much, much smaller than this, but here are the protons that make up nitrogen, and there's some neutrons in there. And then we have an inner shell that contains 2 electrons. We call that the 1s shell. Then next we have the n = 2 shell. The 2 shell is split into 2 subshells, an s, which is the inner one, and then a p, the outer one. The inner one has just 2 electrons, and the outer one, in this case, has 3 electrons. So that would be our shell model picture for nitrogen. Chemists use shell models a lot because it's easy to explain how many valence electrons you have. You can think about things like the size of the atom, the ionization energy, the attraction of an electron in the outer shell to the nucleus based on how far it is from the nucleus and using Coulomb's law. So it turns out to be very useful. So here's just a little summaries of our shell model. So electrons are located in spherical shells, increasingly larger distances from the nucleus. Our shells are numbered with integers like 1, 2, 3. Each shell is divided into subshells labeled with letters S, P, D, F, G. How can you tell how many subshells a given shell will have? Well, it has the same number of shells as its shell number. So if your shell number is 1, then you're just going to have 1 subshell, the S subshell. If your shell number is 2, then you're going to have 2 subshells, the S and the P, and so on like that. So then we learned that from looking at photoelectron spectra, we could, rather than drawing pictures like that, write out electron configurations. So here are the electron configurations of the period 3 atoms, beginning with sodium and working our way across that row of the periodic table to argon. So this is the full electron configuration, but what we notice is that this thing that's in square brackets, 1s2, 2s2, 2p6, is the electron configuration for neon. So as a shorthand, we write condensed electron configurations often, where we just put the next nearest noble gas. So find your element, work your way backwards on the periodic table by atomic number until you find the next nearest noble gas that you've passed, and just put that noble gas in brackets. So this means has the same electron configuration as neon, which is all this stuff. It just saves having to write it. So this bit right here is just sort of the valence electron configuration. And so it shows how we step through across that row and we add 1 electron to each of these subshells until they are full. Here's a picture showing the different blocks of the periodic table. So along with helium, these first 2 columns of the periodic table, the first 2 groups, are called the S block. This middle group right here, this is called the D block. This block over here on the right is called the P block. And down here, the intertransition elements, also called the rare earth elements or lanthanides and actinides, are the F block elements. And so we begin filling F subshells, D subshells, P subshells, and S subshells in those corresponding blocks. And if you look in this picture, it has the outer electron configurations of these atoms, just the valence electron configuration. So hydrogen's 1s1, lithium 2s1, sodium 3s1, and so you see the pattern that all the elements in the same column have the same outer electron configuration. And that's generally true. If we pick something like this column of the periodic table, we see that nickel is 3s2, 3d8, but palladium has an exceptional electron configuration from its photoelectron spectrum. It's 4d10, so it has an unusual electron configuration. We might have expected it to be 5s2, 4d8, just like nickel, but it's different. Then we look at platinum, it's different still. So it's 6s1, 5d9. So there are some exceptional electron configurations, and we figure that out just by looking at the photoelectron spectra. But it has to do with that is the arrangement of electrons in the atom that is the most stable, that gives you the lowest energy. And to help us remember how to fill the electrons in the right order, so which shell and subshell do we start putting them in? It seems like they kind of get out of order. We use this little trick. So we just label rows with the different shells, the 1 shell, the 2 shell, the 3 shell, and the 4 shell, and then we indicate their various subshells. So the 2 shell only has 2 subshells, the S and the P. The 3 shell has 3 subshells, the S, the P, and the D, and so on. And we just start drawing these diagonal lines at the top. 1S comes first, then 2S, then 2P, 3S, then 3P, 4S, then 3D, 4P, 5S, and so on like that, working our way through the periodic table. And this will tell us where to put our next electrons. So we keep filling up a subshell until it is full. Remember that the S subshell can hold at most 2 electrons. The P subshell can hold at most 6 electrons all total. The D subshell can hold at most 10 electrons all total. The F subshell can hold at most 14 electrons all total. Again, we're adding 4 each time, starting with 2, to figure out the maximum number of electrons in that subshell. So this model, our shell model, works very well, but it's what we call a qualitative model. So it gives us pictures where we can explain trends, quantitative trends in fact, but we can't actually calculate numbers from it. So we can't calculate an ionization energy. We can't calculate a radius. We can't calculate properties of atoms that we might want to be able to calculate because they're things that we can measure. So we actually need a more sophisticated model, a model that is quantitative and will let us calculate properties of the atoms. Now we're not going to use that model to do the computations, but we're going to look at the results because it turns out they're important. So it turns out that electrons behave in ways that are wholly unlike anything that we experience in ordinary everyday life because they are so small. And it was discovered with some experiments back in the early 1900s that electrons, in addition to being thought of as particles in certain experiments, that there are other experiments that you can do where they behave like waves. So we know one property of waves is that waves undergo a process called diffraction. They interfere with each other. Well, experiments were done to show that electrons, and actually other small particles like nuclei of atoms and neutrons, can diffract each other. So an electron can diffract itself. There's a diffraction pattern associated with electrons. And that's a property that waves have. So here's a really interesting picture, an experiment that was done using atomic force microscopy and scanning tunneling microscopy. So on a platinum surface, these big mounds that you see right here, those are iron atoms, individual iron atoms laid down in a ring. On the surface, then, trapped inside this ring, we have an excess electron. And this image of a scanning tunneling micrograph shows the wave nature of that trapped electron. So it seems to be spreading out around this ring and waving. So that's proof that electrons, in fact, have a wave nature if you do the right experiment to measure them that way. So we need a new model that doesn't treat electrons like little particles orbiting around the nucleus in shells, but something more complicated. Now, we're going to gain quantitative accuracy. We can calculate stuff, but the problem is we're going to lose a lot of easy interpretations. So we won't be able to draw simple pictures of what the electron is doing anymore because it turns out it's much more complicated. So let's talk a little bit about what that new theory is. So that new theory is called quantum theory. It's also known by the moniker quantum mechanics, and people will often abbreviate it QM for quantum mechanics. So mechanics is just any branch of physics that deals with the motion of things. And so quantum mechanics is the branch of physics that deals with the motion, the behavior of very small particles, things like atoms, electrons, molecules. So as I've told you, small particles in certain experiments behave like waves do. So it was in 1926 that, based on those ideas, that Erwin Schrödinger proposed a wave equation for particles. So wave equations were known in physics for a long time to describe the behavior of actual waves, like on the surface of water or in a violin string. But this was a new wave equation because it was the wave equation that was appropriate for particles like electrons and atoms. And so Schrödinger applied his model equation, his wave equation. So he solved his model, and I call it a model. Oftentimes we've been thinking about models as pictures that we can hold in our head, Now this model is going to be not something that we can hold in our head exactly. It's going to be a mathematical equation. So it's a mathematical model. So he solved this equation for the hydrogen atom, and he was able to show a couple of things. So first he was able to show that the energies are quantized. Well, duh, Bohr had already figured that out. Looking at spectra, and Bohr's model showed that. But it was nice and refreshing that his equation got what we expected, so that energies are quantized. And that's true of all small particles whenever they are bound in some way in a force field. So now we have to kind of give up on this idea that an electron is in a particular orbit or in a particular shell. Because it turns out when something has a wave nature, it kind of spreads out in space, and we're not sure exactly where it is. So you have to do an experiment that treats it like a particle to figure out where it is. But if it's spreading out like a wave, you're not sure about its exact location. So we have to give up these nice pictures that we had of electrons in shells. And now the equations tell us that we can only determine the probability of finding an electron at a certain location around the nucleus. So we can't know its exact location, like is it on a particular ring or in a particular shell located some distance from the nucleus. All we can know is how likely is it to be in a particular region of space. So we're looking at probabilities now instead of absolute things. The other thing that Schrodinger showed is that different energies correspond to finding the electron in different regions around the nucleus. So just like we saw with shells, right, the higher the shell, the higher the orbit, the higher the energy of that particular electron. And so we can imagine that that electron is in different shells. So in this case, we see the same thing, that these regions of probability around the nucleus are different and that they correspond to different energies. So these regions that I'm talking about where you're likely to find an electron, so regions of distinct probability where you're likely to find an electron, these are called orbitals. So another definition for an orbital is a region in space where you're likely to find a particle, an electron. And for the quantum mechanical model of the hydrogen atom, it turns out that these different orbitals are defined by different sets of 3 quantum numbers. So how do you tell these different orbitals apart? Well, before we were using shell numbers and subshells to tell the different shells apart. Now we've got a situation where these different regions, these orbitals that are kind of like our shells or orbits that we were talking about before, we're now calling them orbitals because they're sort of generalized regions. Well, they're defined by sets of 3 numbers. So that's how we can tell them apart. So it's kind of like an address, a label. So we know which orbital we're talking about by the quantum numbers that define that orbital. So let's talk about these 3 quantum numbers because they turn out to be pretty important when we're talking about the atom. So the 3 quantum numbers are shown here in these first 3 rows on this table, and they each have a name and a symbol. So we're going to kind of go through these. So the first quantum number is called the principal quantum number, and it's given the symbol N. And this corresponds exactly to the kind of shells that we were talking about before. So when we used shell number in talking about the periodic table, it's going to mean the same thing as N, principal quantum number. Now this principal quantum number can take on certain values, and this is important in the mathematics of Schrodinger's equation, and those values are integer values. So they start at 1 and go up in integer steps all the way to infinity. So 1, 2, 3, 4, and so on. So they can't be 0. So that's the principal quantum number. So what does the principal quantum number tell us? Well, over here it gives us the meaning. So the principal quantum number tells us the size and the energy level. So just like we saw with shells that had bigger shell numbers were bigger shells further away from the nucleus. So they tell us size of the orbital, and they also determine the energy level. For hydrogen, the energy depends only on N, which shell you're in. For other atoms on the periodic table, it will turn out that it also depends on the energy of those electrons, also depends on another quantum number, which tells us about the subshell. So the next quantum number is called L, and I usually draw that in script form. Here it was typeset as just sort of a lowercase l, so it's kind of hard to tell what's going on here. But I usually draw it as a script L like this, and it's called the angular momentum quantum number because it has something to do with the properties of the electron orbiting the nucleus, and in physics that orbital property is called angular momentum. So angular momentum quantum number can also take on only certain allowed values. It can be as small as 0, then it goes up in integer steps all the way to n minus 1. So once you've fixed what n is, so if n is 2, L can only take on certain values. And we'll see an example of that up here in this chart. I'll go back to that in a second. So if n is 4, say the n equal 4 shell, then n minus 1 is 3. And so L can only take on a maximum value of 3 if n is equal to 4. Okay, so this is going to be a little bit funky because these quantum numbers depend on each other. So the principal quantum number kind of sets the stage, and then the other quantum numbers depend on that. So the next quantum number is called the magnetic quantum number, and it deals with certain magnetic properties of the electron. So it's called M with a little subscript L on it, and it takes on values from negative L, and then we count up in integer steps through 0. That's supposed to be a 0 there. Then we do plus 1, plus 2, and so on, and we can get as large as positive L. So once we know what value of L we're talking about, and there are only some that are possible, we'll know the possible values of M sub L. Now there is one other quantum number called the spin magnetic quantum number that we're going to talk about later, so don't worry so much about that right now. It is about another property of the electron besides mass and charge called spin, and we'll learn about that in another video. So what do these different symbols, what do these different quantum numbers tell us? Again, n tells us the size and the energy level. The angular momentum tells us the three-dimensional shape of the orbital. So this region of space where it's likely to find an electron, what kind of shape does it have? Does it just look like a blob? Does it look like a sphere? Does it look like a cone? Does it look like Homer Simpson? No, it doesn't look like Homer Simpson. But the shape is given by this L quantum number. So if the L quantum number is 0, we're going to associate that with the letter S. So we're talking about the S subshell. If the L quantum number is 1, we're going to associate that with the P subshell. So there's this little code here that we use to go between L quantum number and subshell label. So the subshell is telling us, the L quantum number is telling us which subshell we're in, S, P, D, or F. And it turns out that the S, P, D, F subshells in hydrogen atom and other atoms have a particular kind of shape, three-dimensional shape. So the region in space where you're likely to find the electron has a particular shape. The magnetic quantum number, M sub L, then, is going to tell us about the orientation of those orbitals. So if we've got a particular shape that, say, looks like a rod, is that rod laying on its side? Is it pointing up and down? Is it pointing front, back? That kind of thing. So it tells us about how that three-dimensional shape might be rotated or turned in space. So we call that spatial orientation. So spatial for space, orientation for how it is oriented, right? All right, so those are the quantum numbers. So let's look up here at this diagram that might help unpack that a little bit. So first off, shell is given by the n quantum number. And that tells us what our shell is. Again, shell can be any number 1, 2, 3, and so on. So once we fix the shell number, we've fixed the values that L can be. So let's imagine in this case that n is equal to 4. So if n is equal to 4, the possible values of L can be 0, L could be 1, L could be 2, L could be 3, right? So 0, 1, 2, and 3 are the only allowed values of the quantum numbers when n is equal to 4. Now, if L is equal to 0, that means your subshell that you're talking about is an S subshell. What are the possible values of M sub L? Well, M sub L starts at minus L, goes up to positive L, but if L is 0, then you sort of start and end at 0. So there's only one M sub L quantum number, and that would be 0 if L is equal to 0. Now, if L is equal to 1, the possible values of M sub L, you start at negative 1, you go to 0, and you go to plus 1. Right? N equals 2, then you start at negative 2, negative 1, 0, plus 1, and plus 2. Just like that. So each one of these little boxes that's right here, this is what we would call an orbital. So each box sort of represents a place in space where you would find the electron. Now this isn't what the actual shape looks like. This isn't the region of space. It's just kind of a placeholder. So like each one of these boxes, these three boxes right here, they are different orbitals that are now in the p subshell. All right, so we have our shell, the n equal 4 shell. L is equal to 1, so it's a p-type subshell. And within that, there are 3 different orbitals. What's going to be different about them? Well, they're going to have different spatial orientations because their m sub L quantum numbers are different. And so each one of these guys right here, each one of these boxes, is signifying a different orbital. What is an orbital again? It's a region in space where you're likely to find the electron. And it's analogous to the shells and subshells that we've been talking about before, only much more difficult to picture because it's now a region of probability. So in the next video, we're going to go in and look and see at what some of those shapes are like and look at the different ways of representing the three-dimensional shape and orientation of these different orbitals. So we're going to get some pictures to go along with these things.